Hi everyone, we are Team Goose and we are building Mulaw, the world's first human-like voice assistant. In the last couple of months, we've seen a dramatic shift in how voice assistants are built. While in the past, we'd have these kind of one turn based systems like Siri and Google Assistant, where you could only ask them a simple request like, what is the weather, or schedule a task for me. We've now seen the emergence of these LLM or large language model powered voice assistants like ChatGPT and Rabbit. These new voice assistants enable a whole new subset of applications of voice assistants. Um, and we believe that they're the future of, or one of the futures of how we can interact with AI. But there's a major problem with how these voice assistants are built today. Let's take this simple example. You ask a voice assistant like ChatGPT, can you explain inheritance? The first problem you encounter is that it takes 4 seconds, a really long time, to understand what you're asking before it even starts answering your question, while a human would respond in normally less than a second. The AI goes on to respond, inheritance is a fundamental topic in object oriented programming, blah, 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 blah. And it continues for a whole minute. You have to wait that whole minute for it to stop talking before you can say, oh no, I actually was talking about money inheritance, not the inheritance that's related to object oriented programming. In a real conversation, you would just interrupt this voice assistant. But this isn't possible with how these voice assistants are built today. And so these were the two main problems that we aim to solve when building Mula: high latency conversation and the fact that users can't currently interrupt these voice assistants. So let's take a look at how we built it. Our team is comprised of two members, myself, Jerry, and my teammate, Will. The basic architecture of our solution starts with a really simple sequential model. We start with speech recognition, which takes your input audio and converts that into text. That text then goes into a large language model, something like OpenAI GPT-4, which responds with text. That text then needs to be converted into speech by a text to speech model, and that speech gets played back to you, and then you can respond afterwards. This is a really simple architecture, and there's a lot of kind of low hanging fruit on how we can improve or optimize the latency here. The first thing that we did is we chose really fast components. Something for our speech to text or transcription, we used DeepGram, which responds with transcripts in around 300 milliseconds. This is significantly faster than something like Google speech to text, which responds in normally over a second. We also used a really fast LLM hosting platform called Grok. Grok responds in around 400 milliseconds, while something like GPT-4 would respond in well over a second as well. We then use DeepGram Aura for our text-to-speech, which responds in around 400 milliseconds. This is, again, significantly faster than most text-to-speech models out there, which normally respond in over a second. So just by choosing really fast components, we've kind of reduced latency to around the scale of a second. The next problem that we aimed to solve was the fact that users can't interrupt this current flow. In this current flow of data, you would have to wait for the LLM and for all this processing to happen, and you'd have to hear everything they said before you can respond again. And so the way that we solve this is we actually listen to the audio from your microphone all the time. Instead of just listening after the assistant has stopped talking, we're listening to what you're saying continuously. And whenever we hear that the user speaks and we get a transcript from our transcription model, we just cut off the assistant, remove any audio in the audio buffers, and we basically interrupt the assistant. The technicals of how this work is a little bit complicated, but we're going to keep this all high level for now. One of the problems that we were facing when we initially deployed our model is that the assistant would hear itself and stop speaking. This was because we deployed our service to a web browser. And in web browsers, there isn't any automatic echo cancellation. And so this was a problem that we didn't expect that actually became a significant issue when we were developing our first test cases. The solution that we ended up coming up with is hosting our AI voice assistant on a telephone number instead of in the browser. This allowed people with any kind of cellular device to be able to use our voice assistant. So more people can use our voice assistant now. And also, telephones, surprisingly, have built in echo cancellation. We used a service called Twilio to manage our phone number and connect to your phone number, and our code runs on Heroku. This is basically what our infrastructure looks like. We push our code to GitHub. That then has some CI/CD stuff that's happening there. And whenever we push to our main branch, that gets pulled into Heroku and gets deployed. Heroku connects to Twilio through a WebSocket. So audio is being constantly streamed from Twilio to Heroku, and Heroku constantly streams audio back to Twilio, and Twilio manages that connection with the end user, which is calling from their phone. That's the basic infrastructure that we have today. At this point, our solution was working, but we realized that we could still go faster, reduce latency, and get closer to a human-like conversation. And now will take you through the hacks and challenges that we faced when trying to make our voice assistant just go faster.
So how do we measurably improve our system? A common measurement used for AI voice assistants is voice-to-voice latency. Voice-to-voice latency is the difference in time between when the human stops speaking and when the AI assistant starts speaking. This is an important metric when making a conversation feel more human-like, because lower latency or faster responses is shown to increase people's sense of connection with each other. To see how the competition compares, ChatGPT's AI voice assistant takes around 4 seconds to respond, while another popular voice assistant called Pi takes around 6 seconds to respond. How does ours do in comparison? Well, one issue we ran into is that testing this and measuring this is a little bit difficult. Due to noisy environments, sometimes tests just wouldn't work at all because the assistant couldn't hear us over the noise. Also, tests can be hard to reproduce. So if I were to say something slightly different, the system might respond completely differently and take a different amount of time. And it can be difficult to debug and improve on latency scores when the tests are not identical. Finally, testing is just tedious. It's difficult to say the exact same thing every time, press the start timer button as soon as you finish speaking, and then perfectly react to the system beginning to speak. It's just a difficult process. So our solution to this issue was we automated testing. So instead of using a real microphone and real speaker, we had a setup where we used a virtual microphone and virtual speaker. And we used pre-recorded scenarios. So how this worked is we pre-recorded audio clips of us asking questions to the system and then played them back through a virtual microphone. The system then heard this as if it was a real microphone and then played back its response as soon as it was ready through the virtual speaker. And the advantage of the virtual microphone and virtual speaker is that we can exactly measure when the virtual microphone stops playing sound, and we can measure exactly when the virtual speaker first hears the AI start speaking. And this can give us a very accurate measure of voice-to-voice latency. Using this process of testing repeatedly, we were able to swap out different components in our stack and get a voice-to-voice latency of about 1.2 seconds, which is very impressive. I think the greatest factor in this was our choice of language model, Grok, which just has an extremely fast or extremely low latency. The problem with this 1.2 second number is that it's still about an order of magnitude slower than humans. And in conversation with the system, you definitely notice this difference. So in order to make our system respond faster, we had to try some alternative approaches. So the approach that we tried is response pre-generation. One question we had when looking at the speed of human responses is, how are humans so fast? After all, the average human reaction time is in a similar time range. It's about 200 to 300 milliseconds. So if humans are able to respond as fast as they can react, that must mean that humans think about their response while they're listening. And don't just take our word for it. Research seems to come to the same conclusion. So how can we make our system do the same thing? So this scenario is basically what we want to happen. So while the human is speaking, so if I'm saying, "Hi, I'm Will, what is," the system doesn't necessarily need the rest of the sentence to start coming up with a response. Like it could think of like, "Hello, Will." It could think of the first couple of words. But one question we had when doing this is, when should the system start thinking? Ideally, it would think all the time, but thinking isn't exactly a cheap process, especially with large language models and text-to-speech paying or costing money per word generated or spoken. The research says that humans start thinking about a response when enough context has been given. Unfortunately, it's not very easy to tell when enough context has been given, so the approach we used was to estimate based on number of words spoken. We call this process of guessing when to start speaking midpointing, because we were trying to find the midpoint in the user's utterance. So an example of how this would work is I could say something like, "Hi, I'm Will, what is," and right then the system could think of the first few words of its response and think, "Hello, Will," and I could finish my sentence, "What is your name?" And immediately the system would have already had time to generate its first few words, "Hello, Will," and their speech or text-to-speech equivalent, and play that back immediately. And while it's playing back those first few words, it has time to generate the next part of its response. So it could say something like, "My name is Mulaw." So then from my perspective, I would just hear one continuous response. I would just hear, "Hello, Will, my name is Mulaw," and it would play immediately as soon as I finished speaking. Using this approach, we were actually able to get our latency very close to the human range. In some scenarios, as low as 0.3, in other scenarios, around 0.8 seconds. So what's next? We think what would really improve things is having smarter midpointing. In some scenarios, the first few words of the user's utterance are not enough context. So the system will come up with a silly response like, "I'm not sure what you mean," even though if it had kept listening, there would be enough words for it to come up with a better response. Another thing that we want to work on is better response synthesis. So the way that we actually get the system to come up with two responses is we ask it to start a response, and then we prompt it in the background to please finish its response. And sometimes the system responds directly to this prompt and says something like, "Sure, I'd be glad to do that," and then continues its response. And then the user ends up hearing something like, Hi, Will. Sure, I'd be glad to do that. My name is Mulaw, and it wouldn't really make sense to the user. Um, Part of this better response synthesis is having actual metrics to judge how good a response is, because right now we've just been like sacrificing everything for latency, but there's no real metrics to determine how the quality of the responses are suffering because of it. Um, what about the future of AI voice assistants in general? We think AI voice assistants, at least for the near term, will function similarly to this one, where improvements in each component and approaches like pre-generation will allow pretty good performance. But I think in the future, everything will move to end-to-end models. So this means continuous voice input and continuous voice output from the system. One limitation that's preventing current systems from reaching this is their transformer based architecture. Transformer based models um, look at all the input at once and then can stream output from that, but they can't take streaming input. So that makes something like this difficult right now. Um, Overall, our contributions from this project are one, we created a model or a system with near human state of the art latency. Um, we developed a novel response pre generation technique, and we implemented user interruption.
All right, now let's go through a quick demo of Mula, and I'm just going to give it a call on my phone. Hi there, my name is Mulaw, and I'm here to chat with you about whatever's on your mind. Don't worry, I won't take offense if you interrupt me. I'm designed to help you find answers or have a friendly conversation as efficiently and naturally as possible. So go ahead, ask me anything or tell me what's been going on in your world. Want to play a quick trivia game or get some Hi, Mula. Can we play trivia about the University of Waterloo? Of course, I'd be happy to play a game of trivia about the University of Waterloo with you. Here's a question to get us started. What is the name of the University of Waterloo's official mascot? A. The Waterloo Warrior. B. The UW Kangaroo. C. The Fighting Frog. D. The Golden Hawk. Let me know your Is answer. It A. The Waterloo Warrior? That's correct. The University of Waterloo's official mascot is indeed the Waterloo Warrior. Well done. Here's another question. What is the name of the main student union building at the University of Waterloo? A. The Student Life Center. B. The Waterloo Student Is it the Student Life Center? Yes, that's correct. The main student union building at the University of Waterloo is indeed the Student Life Center. Great job. Here's another Awesome, question. Mula. Let's switch topics really quick. My name is Jerry. Can you please call me Jerry from now on? And can you tell me a little about yourself? Sure, I'd be happy to tell you a little bit about myself, Jerry. I'm an AI assistant developed by Meta AI, and my primary function is to assist users like you with various tasks and answer questions to the best of my ability. I can answer questions, provide information, and even engage in conversation. I'm designed to be helpful and efficient, and I'm here to make your interaction with me as natural and intuitive as possible. Is there anything else you'd like to know about me, Jerry? Yeah, can we talk a little bit about large language models like GPT-4 by OpenAI? And can you tell me how they work? Sure, I'd be happy to explain how large language models like GPT-4 by OpenAI work. Large language models are a type of artificial intelligence that can process and generate human-like language. They are trained on vast amounts of text data, such as books, articles, and websites, and use a technique called deep learning to learn the patterns and structures of language. The key to large language models is their ability to learn from large amounts of data. By training on vast amounts of text, the model can learn to predict the next word in a sentence given the previous word. This allows the model to generate text that is coherent and natural sounding.
GB or biobanize a specific type of large language model called a transformer. Transformers use a unique architecture that allows them to process input
How
sequences
does
of
deep
varying
learning
lengths
work?
and features. Deep learning is a type of machine learning that involves training artificial neural
What is
networks
machine
to
learning?
learn and great question. Machine learning is a subfield of artificial intelligence that involves training algorithms to learn from data and improve their performance on a task over time. In traditional programming, a computer is given a set of rules to follow to complete a task. In contrast, machine learning algorithms
All
are
right,
designed to
let's switch topics again. Can you write a short poem about my name?
Jerry, Jerry, a name so fair, a name that's strong and bold and rare, a name that's associated with grace, a name that's found in many places. In the biblical land of Egypt, there was a Jerry, a wise man, a pharaoh who ruled with wisdom and tact and brought great prosperity to his clan. In the US of A, there lived a Jerry, a famous one, a comedian who made us laugh with glee. A man named Seinfeld, a legend you see. And now here's a Jerry, a man of the modern age, a man who's smart and kind and witty, a man who's always on the stage. So here's to Jerry, a name that's strong and true, a name that's associated with great things, a name that's welcome everywhere too.
Awesome, Mula. That is it for now. Thank you for your time today. I'm gonna go now. Bye bye.
You're welcome, Jerry.
Awesome. And that was a quick demo of Mula. There were a lot of small tidbits that you could notice there. For example, when it responded really quickly, that would be an example of pre-generation or preemptive generation. And you could see that sometimes it would do this pre-generation incorrectly, and sometimes it would respond incorrectly. But it would eventually correct itself later on. And so that was a quick demo of Mula. Thank you. Bye bye.